We are going to next combine sections 8.5 and 8.6 into one because they're a very similar reaction. 8.5 is called hydration by Oxymercuration-Demercuration. And section 8.6 is called Alkoxymercuration-Demercuration. So the first reaction, the hydration reaction that we're going to study, is also another way to essentially add water to the alkene. So you're going to turn an alkene into an alcohol, just like the reaction that we looked at in section 8.4. The oxymercuration-demercuration process gives us the Markovnikov product, just like the mechanism in 8.4, the acid-catalyzed addition. But this mechanism prevents rearrangement, so it's beneficial. If we look back at the reaction, the first reaction that we did in section 8.4, if we had wanted to use this reaction to put an OH group right here onto this alkene, these reagents wouldn't do it for us because the rearrangement is always going to occur. If we wanted to put the OH group in that spot, the Markovnikov product, without allowing for rearrangement, we can use the Oxymercuration-Demercuration reaction. So this is Markovnikov addition. Put the hydrogen on the carbon that has the most hydrogens already present. We put the OH on the other carbon. It has no rearrangement ever. Which gives us more control over the product. And also, the OH group and the hydrogen that are added to the alkene go onto the molecule in an anti-configuration. So we call this an anti-addition. That doesn't mean anti-addition doesn't mean not addition. It means that the hydrogen and the OH group add to the alkene anti to each other. The mechanism for this reaction we're not going to study. We're not going to write it out. That doesn't mean that it's not interesting. But it is in your textbook, mechanism number 8.5. And in one of the editions, I'm not sure which one, it's on page 333. So it's either going to be there or about there. I don't have my textbooks with me, so I can't tell you which edition that's accurate for. And so I do suggest that you take a look at the mechanism, and just the mechanism, seeing the mechanism will help you understand why there is no rearrangement for this reaction. So let's take an alkene and do a general reaction here. The reagents for this reaction are more intense than any reagents we've ever seen before. We do this reaction with mercury 2 acetate. The abbreviation that we use for acetate in organic chemistry is OAC. And there's two of those. The acetate is just the acetate ion, CH3COO-, and we put that in water and put that in with the alkene, and that's a step 1, so that's on its own arrow. And after that reaction is done, we follow this up with a reagent called sodium borohydride, NaBH4, which is just a second step of the reaction. We're going to learn a lot more about sodium borohydride next quarter, but for now, these are just the series of reagents that give us the desired product. And in this case, we're going to get the OH group going where we want it to go. So it's going to end up, I think I totally did that backwards. Cross that out. Yeah, I put that anti-Markovnikov. No, now I'm making an alkene. Okay, so this carbon had one hydrogen present. We're going to put the second hydrogen there. We're going to put the OH group down here and the hydrogen up on that spot. It is a Markovnikov. And the hydrogen and the OH group added anti to each other in this molecule. In this particular molecule, it doesn't make a difference at all because we don't have any stereocenters at all here. But if there was stereochemistry in this molecule, it would make a difference. Let me draw you a slightly different alkene, which is a little bit more generic. Those bonds on the carbon are not intended to be ethyl or methyl groups. They're just empty bonds. They could have anything present on them at all. And again, I'm just doing this to show you the anti-addition. Your OH group and your hydrogen are going to go opposite each other in terms of configuration. That's going to be a big deal if you have stereocenters in the final product. You're going to make specific stereoisomers or mixtures of enantiomers. Now, the Alkoxymercuration-Demercuration reaction is very similar to this mechanism. It uses the same kind of reagents, and it produces the same kind of product following the same rules. It's a Markovnikov addition, no rearrangement, anti-addition. The only difference is that instead of using water with your mercury 2 acetate, you use an alcohol. And we're just going to say ROH. It could be anything. That R group could be any kind of alcohol at all. You follow it up with sodium borohydride, just like in the oxymercuration-demercuration. And the product that you make is not going to be an alcohol. It's not going to have an OH group on it. It's going to have an OR group on it. What's actually being added to the alkene here is this water molecule. So a hydrogen is going on one spot, the OH group is going on the other. In this case, you're adding an alcohol to the alkene. So you're going to be putting a hydrogen in one spot and an OR group in the other. It's basically exactly the same reaction with just one slightly different reagent. And again, it's going to be Markovnikov, and it's going to have anti-addition, just like the oxymercuration-demercuration reaction. And again, this is only going to be, the anti-addition aspect of it is only going to be an issue if there are stereocenters in the product. So in the next video, I'm going to do for you a whole bunch of examples of the oxymercuration-demercuration and the alkoxymercuration-demercuration.